Hello students. We're going to now introduce linear combinations of vectors and span. So I have to say what these are. A linear combination of the vectors v1, v2 through vn. So we have some finite collection of vectors, and a linear combination is just a sum of the form a1 v1 plus a2 v2 plus dot 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 an vn for some ai in our field, which could be whatever. So a linear combination is just a sum of this form. Some multiple of the first plus some multiple of the second plus some multiple of the third, and so on. For example, if you only had one vector, what would you get? Well, you would get all the multiples of a single vector. Okay. Now what span? The span of the set v1 through vn, which is, we're just going to write it. We'll put an open parenthesis and we'll do that. And that's just going to be the set of all linear combinations. Of the vectors v1 through vn. So we have some collection of vectors. We know what a linear combination is. It's a set of, you multiply them by constants and you add them together. That would, any way you can do that will be a linear combination. So what we have here for the span is we have every possible linear combination. So every possible one that we can make up, regardless of what constants we pick, that's all going to be inside the span. Now the span ends up being a vector space, which is not a given. We have to show it. So let's try to show it. So the span is a vector space. I mean, it's also a subspace because it's going to be contained in whatever space v1 through vn exist in as well. So I could have said is a vector subspace, but a vector subspace is a vector space, and if it's a subset that's a vector space, hopefully by now you also know that it's a subspace. The language is convenient in that way. Okay, so the span of these vectors is a vector space for any vectors we pick. And throughout all of this, we're just assuming V is some vector space over some field F. Okay, so let's prove it. Proof. Well, what do you have to do? Well, we have to show that it's non-empty and has two properties, or we have to show it contains the zero vector and has two properties. Either one of those, I mean, doesn't matter. Let's show it has the zero vector in it. Well, the zero vector is going to be equal to 0v1 plus 0v2 plus dot 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 0vn, and that's a linear combination, so we're done. So what that shows is that 0 is in the span. Because the span is the collection of all linear combinations. Okay, so now what do we have to show? We have to show it's closed under scalar multiplication and addition. So suppose x and y are in the span. What does that mean? It means they're both linear combinations. So then what can we do? Well, we could just write them. Right? X is going to be equal to a1 v1 plus a2 v2 plus an vn. And you know, you can write the first two terms, you can write the first three terms, you can write the first term and you put dot 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 and you end with a and vn. I know what you're talking about. What do we know? We know that y is also a linear combination. So I need new constants. I'm going to use b for those. Same vectors though, because it's in the span of the same vectors, right? So I don't have any different v's. I just have different constants. B2, V2 plus dot, 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 Bn, Vn. Okay, so we have these two elements that are linear combinations because they're in the span. What happens if we add them together? Well, what's going to happen? I get this plus this, right? And because of the distributive law, this is just going to be so as you see, I guess I could have written an intermediate step in there, but hopefully you guys see A1, V1, we're going to add that to B1, V1, use the distributive law, we can write it like this. So what do we have? Oh my gosh, these are all in the field. This is in the field, this is in the field. What do we have? We have a linear combination. So it's in the span. And that's what we wanted to show, because we're trying to show that the span is closed under addition and scalar multiplication. So let's do that next. If lambda is in the field and x is equal to a1 v1 plus a2 v2 plus dot, 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 an vn, I want to show that after we multiply, scalar multiply, we will still be in the span. And how do we do that? Well, I take lambda times this, and I think you guys might be able to see what's going to happen here. Well, this is going to be lambda a1 times v1 plus lambda a2 times v2 plus dot, dot, dot. I'm going to squeeze this in here, lambda an vn. Okay. So what is this? Well, this is in the field, and this is in the field, and this is in the field. So what do we have? We have a linear combination of the same vectors, v1 through vn. So lambda x is also in the span. So we've shown that the span is closed both under addition and scalar multiplication, and we know it's non-empty. So that's all we have to show to know that the span happens to be a vector space. So if we take any vectors, we can form the span. So any vector space, any finite set of vectors, we can form the span. The span will always be a subspace. It'll be a vector space of itself. So maybe it'll be the entire thing. Maybe we picked a bunch of vectors and we got the exact same space back. Maybe we picked some vectors and we didn't get all of V when we did that. There are certainly plenty of examples to look at of both. But the span has a special property which I think we should prove next, but let's do that in the next video.